Let's begin by describing PTC Creo. PTC Creo helps teams create, analyze, view, and leverage product designs downstream. And for today's presentation, we'll see how PTC Creo can simulate your product and help you make design decisions early in the design process. PTC Creo is scalable. It enables each user to take advantage of a tool that is right for their work and their role so they can get design information critical to their needs. It gives them the ability to the right level and detail of information without recreation of data. PTC Creo is also interoperable, which means that each of the tools within the PTC Creo suite provides a different view of the same data, the same single source of truth. So for today, we'll be looking at the simulation perspective. And finally, time to value. For existing users, the benefit of PTC Creo is also about protecting your investment. Everything is still there, no regressions, no data migration or conversion. It's 100% compatible with new capabilities that will make you more productive. So let's talk about PTC Creo Simulate now. The lack of early design insights impairs product designs. Everyone agrees with this basic statement. But here are a few statistics that we found from some industry survey results. Companies that are lagging in simulation miss targets. 48% are more likely to miss product cost targets, and 46% are more likely to miss product quality targets. These are big numbers that have large financial effect on a product's launch. So identifying problems earlier is much more impactful. The final statistic here backs this up by saying that 73% say that most critical decisions are early in the design process. And PTC has a solution for this. It's called Creo Simulate. And when you put our solution to work early and often, it has a very big impact. So here's some proof from some additional research. When you look at industry laggards, they see their development costs 11% higher, and warranty costs and ECO costs are 6% higher when they don't adopt engineering simulation. But for the respective industry leaders that do adopt engineering simulation, they see their development costs at 3% lower. Their warranty costs are 7% lower, and their ECOs after design release are 4% less. So simulation will always enable the designer to make better decisions early in the process. Here's a good visual explanation of this with the product design process on the horizontal axis below and the cost of change on the vertical axis. Companies that can reduce their development costs when they focus on analysis-led design by doing simulation early and often in the design process when the cost of change is low. So you'll always be able to make better decisions that will lead to a higher quality result. So by the time you get to the prototype and the test phase of the design process, you'll pass with flying colors because you understand the product's performance already based on all the early simulation you did early in the process. PTC Creo Simulate and Advanced Simulate are two extensions that are available as PTC Creo apps. These two are the proven flagship products that PTC has been developing for over 20 years. Here's a small list of the incredible capabilities that PTC Simulate contains, starting with structural, thermal, vibration, and buckling, and the list goes on and on. All these solutions are focused on helping companies understand product performance and optimize their digital design. My final slide here just gives a little list of a few of the checklist items, and you can get a very thorough data sheet from ptc.com on all these extensions. But the first column here next to capability is the entry-level product that it's available on every seat of our software, and this is free. It does very basic simulation and it's limited by model size. Next is the simulation extension, and finally advanced simulation. So this is not an exhaustive list, but it gives you an idea of the insight that you might need to identify which product would be right for you. So for example, if you want to do large deformation with nonlinearity, well then advanced simulation is where you need to be. But if you do very basic stuff with solid elements and you want to do some optimization, maybe a little nonlinear contact, then simulation extension is all you would need for that. So let's begin our live demonstration now with a few models. Today we'll be using these three RC vehicles for our data set. We have a quadcopter here. We have a hexacopter right there, and then we have a hexacopter with a Y configuration there. So we'll be using this as the content to show you simulate, do a few scenarios, and hopefully inspire you to how you can use simulate in your company. Let's open up the quadcopter as well first. What we're going to look at with this one is we're going to identify what kind of stresses and vibrations are being exposed in this little support bracket. Okay, so let's open that by itself. Creo Simulate's very simple to learn and use. I'm going to simply just go into simulate now with this part. The material has already been defined as aluminum. That can be done at the part level before you come into simulate, or you can do it here. What we're going to do for this part is we're going to just say that these 3 locations are held fixed, just like we would do in a physical test lab. That's all done. And for a modal analysis, that's all I need to do. What I will do though is I want to also run this as what are called shell pairs. I'm going to say make my shell elements 17 pairs were automatically done for me automatically. So now if I want to just mesh that, I can see what those elements look like. So very quick to get to a mesh. Now we're going to just define an analysis. We'll say a modal analysis. We'll give it a modal 1 name. And let's say we're going to run get 6, for example. And hit OK. It runs with these shell elements, so it's going to run very quickly. It's already done. So we can close that out and go to our result. Let's go ahead and input our result from a template. There's modal 1. That's what we want to see. Our template's right there. Let's go ahead and check all these boxes for all 6. Now we'll see our 6 mode shapes and the respective natural frequencies next to each mode shape. So this is the shape in which it moves. So the first one is more of a bouncing, and we have some twisting on the rest of them. So now we can make a judgment based on this data if we're in the right category of frequency, so that we're not going to be interfering with other electrical components in our model. We can also take that and get full dynamic time, dynamic frequency spectrum as well if you want to go a little further into the vibration world. So also on this model, let's go ahead and look at stresses. What I want to do here first is I want to apply a load onto that green surface, but I don't want to apply a load to all that surface. So I'm going to break it up with what's called a surface region. You can do surface regions, or you can also do volume regions. I'm going to say sketch on this surface right there. Hit OK. And let's go ahead and just make a rectangle right there. And now what I can do is go ahead and apply a load to that surface by itself. And we'll give it our units that we want to use is pound force, and let's give it a negative y direction. Set up our analysis and say it's going to be a static analysis, and just call it static 2. And our convergence methods there's 2 of them available. One is multi-pass, one is single pass. Single pass is our proprietary method at PTC, where we run the model at one element edge order, and then we adaptively change where necessary, either higher or lower based on the first run, and then we run a second time. Multi-pass is our traditional method, which is, again, the traditional method of FEA. It will add more elements to a mesh to make sure it converges. What PTC does is we add more math, higher level polynomials, and we keep on adding more math until we converge on the criteria you want to converge on. So I'm going to say single pass though. That's what most of our companies and customers use. I'm going to say OK and run. It's going to use, again, the shell elements. It's going to run very quickly. It's already complete. And now we can look at the results of this one. Let's look at stress, KSI, and animate as well. So actually very low stress for this part, but we can kind of see where the weakest points are on our model. All right, so that's it for that component. Let's go ahead and look at maybe a more sophisticated assembly. Let's close out of here. In the quadcopter by itself, one of the nice things about integration with Creo is that the FEA tool is connected. So whatever I'm working with in my assembly, I just take it over to simulate really quickly. So I can change my simplified representation to this structure, and then I can go take this over to simulate. It's hierarchical, so I have some constraints and displacements here that are part of my part level, so I could include those or not include them. But the point here is that I want to show you how easy it is just to, at this level, I have an assembly, it's assembled together, how the designer wanted it assembled, and I can go in here if I want to and remove things and change things. But because Simulate is so simple, most of the time I don't have to. I can just go in here and say, you know, I want shell elements for the entire assembly. Pick the entire assembly, hit start, and then 59 shell pairs were just created instantly. Okay, so now if I want to do a review on that, I'll see now my entire assembly with shell elements, but I will also see that because it did shell elements, which is mid-planing the geometry, it also connects everything with these little rigid links, these magenta colored rigid links. So now I don't have to put the assembly back together with welds and so forth. It does it for me automatically. Huge time saver and great accuracy, great improvement for any other, the types of these studies in the past used to be a while to actually set them up, but I just set the whole thing up in just a few seconds. This one does take about 5 minutes to run, so I'm going to go ahead and look at the results here that were run. I'm just going to look at the modal analysis, and let's just look at the model displacement for the first mode shape. So you here have your natural frequency. This is the first mode shape. Its tendency to move is just a kind of a teeter-totter effect there. And then I could look at the rest of them as well. You can see right here is all your different frequencies right there for the first 4 anyway. So that's how easy it is to get from a weldment into a simulate study. Let's go ahead and close that. And the next thing we'll do is just, what if we want to pick just that one frame member all by itself? Okay, again, really simple. I bring it open inside of simulate here. I have my material already assigned. I'm going to pick on displacement. I'm going to pick on a few surfaces on both of these. And then I would pick these bottom surfaces as well. Even though these surfaces are going to get compressed, I'm able to pick them because Creo Simulate's smart enough to know that there's an edge there. Now, if I wanted it to be extra cautious, I'd go ahead and only pick edges, but it's not necessary. So that's good enough for those surfaces. And then I can also pick on a force, and I can say this surface there, and again give it a negative value here. There we have our force on there, our constraint. Again, just like I'm building this in a physical test lab. I've applied everything, and now I can go ahead and run it. But before I do that, I need to also make sure that I, again, detect shell pairs. I can't stress out how nice this is. You know, it's automatically just geometry based. This could be just regular IGES files or step files, and I could still read it and geometrically identify shell pairs really quickly. Set up my static analysis, call it frame 1, okay. Again, what Creo Simulate does is it goes ahead and meshes it first, runs it through a first pass analysis. Again, there's almost 30,000 elements in this one. After the first pass, it adaptively changes the element edge order where appropriately needed, and then it runs a second time, and then I have my analysis complete. And let's just look at displacement here. You should always check out displacement first, make sure it's moving the way you would think it would. In this case it is. So we're moving about 2 millimeters, which is about right. It's a pretty stiff frame. All right, so I hope I explained on the quadcopter how to use Simulate. We'll now move on to a couple other components. For our next use case, we're going to look at the Hexacopter here. And what we're going to look at is the battery mount here. Okay, so this little cover here will go ahead and clip onto this part right here. So we're going to check out the fit and check out if everything's going to work correctly there. Now these parts will be 3D printed, so you want to make sure that we have confidence that once we make these parts that they'll function correctly. Okay, so for this simulation, I'm going to go ahead and run here's that battery and support there. I'm just going to run it as a quarter model here. And what we're going to do is we're going to push this component this direction. Okay, so let's go into simulate for that. And we're just going to put a force over here, actually a displacement. And we're going to say that's going to move in the negative 11.7 millimeters. Okay, and then we just define lots of different areas of contact. Okay, so there's one contact, there's one, there's some more. So every part of the two components that come into contact, we're just defining regions that says that those two components are going to be in contact in those different areas. And then as we see this part move in that direction, in the Z direction, you'll notice that it'll go ahead and come into contact with all different areas. So the results here look something like this. Let's look at this example here. On the left here we have stress. Let's start that up here. And we're just looking at large deformation with contact, really. On the right we have displacement. And we have it just before it actually goes down into that area. So if I hit pause here, there's our final step at the max displacement and max stress of the model. Okay, so large deformation with contact, we can see our stress actually doesn't get too high with respect to this material, so it's probably we're pretty safe there. It is a linear case here. Now, if we want to get into even nonlinear materials as well, we can do that with this example right here. Here's just a simple little tensile bar, and we have it with a force on one side and we're holding a fixed on the other side. But I want to show you the materials here. The material definition, what we can do hyperelastic, isotropic, or elastoplastic. So if we say elastoplastic, and I say edit here, I can go ahead and put in my own values for plastic strain versus true stress here. Okay, and this is what it's going to look like once it's reached the nonlinear state. Okay, this is the it's a linear type of problem until it hits that stress level, and we can have it choose linear hardening, power law, or exponential law, or I can choose it myself. Okay, so we run this thing. It just takes really quickly to run it. Let's just go ahead and set it up here. I'll do a new one, a new study. I'll just call it new. How about that? And then we'll say nonlinear contact, or sorry, large deformations with plasticity. And let's just say quick check this time. And I'm going to go ahead and say, let's go ahead and do 11 steps and space equally. Okay. Once I do that, I can run it. It's going through past step 1, 2, 3, 4, 5, 6. And then right here you can see it actually tells me that plastic deformation has occurred. And now it's going through the next 4 steps after plasticity, and it's also going to let me then it's going to use those material definition. I used it earlier in my definition for the material. So I also didn't point out, but I also have some measures here of stress and strain on my model. So when I go to results here and I look at new, I can do this and say, let's look at deformed 1%. That's good. So here you can see I'm in a plastic range here. My stress is very high. But what I want to show you is that I can also graph let's see, would pick stress on that axis and strain on this axis. And now we can see how it reacted. There's my stress strain graph. Okay, so we can do nonlinear materials. We've been able to do it for a little while now, and with great accuracy. Our last example here, it will be focusing on some design aspects. So we're going to use the Y configuration, the hexacopter, for this one. And again, just like before, I'm just going to make a simplified rep here of the frame. Actually, here's the entire frame here. And we could go ahead and run it like this if you wanted to. But I'm going to go ahead and pick one of the segments here and hit OK. And what we want to do here is I want to go to simulate with this. And I've already set up my analysis. I have my shell elements already done, and I've got my forces on there, and I've got my constraint. Okay, so I wanted to look at, what if I just run this like this? Okay, I've got no reinforcements in there, no spacers. I have it just like this. Compared to if I want to run it with simplified rep 2 here, I want to use a couple of plastic reinforcers in there. And these are 3D printed parts, and I want to put those, the red and the yellow part, in there for some additional stiffness. Okay, how will that affect my final design? again, when I'm at a very early stage in the design process, I can just kind of do these what-if scenarios and say, what if I do that? What actually will happen? And again, these simulations are very quick, very simple. I'm just going to share the results. They take less than 2 minutes each to run. Let's go ahead and open up the wireframe 1. And I'm just going to look at displacement. This is without the reinforcements. We see we're at about a 10 millimeter displacement there. Okay, obviously at the ends is where the displacement is the greatest. If I open up the wireframe 2, which is everything's the same, I just want to look at, again, displacement is good and deformed. This is with those reinforcements in there. Notice now it's using, solid elements for that area. You can see compared to over here, you have the, it's a gap. Over here, you can see those parts are in there, as well as you can see them in there as well. Okay, so looking at the two comparatively, the left we have again our original is about 10 millimeters for displacement. On the right, we're at under 5, so we've reduced the displacement by a half just by adding those two parts in there. Again, this is great insight to understand, well, how much will it change? Now you can maybe play with different material types and maybe different shapes you can play with to really try to hone in and making these design choices and really doing what's called analysis-based design. So I hope I've showed you a couple of scenarios that will inspire you of how Creo Simulate can be used in your company.